All right, so again, Paul Anderson with Adams. So as she mentioned, Adams is a value-added distributor around pneumatic, hydraulic, and automation components. Been in business a little over 60 years based in Tampa. We were able to expand into Alabama about 2.5 years ago and started working with a lot of the manufacturers here. Myself, as she mentioned, Vice President of Sales with Adams. Started with the company about 14 years ago and really have been working in the dust collection space for about 9 years now. Needed to prove it with a picture of me working on a dust collector too, to give a little bit of validity to it. So my goal for this presentation is really to discuss dust collectors and its operation, not knowing everybody's background, really gonna go into kind of the guts of the dust collector and then kind of the impact from a sustainability and energy standpoint as well. What we're typically seeing from operational inefficiencies, the energy demand of these systems, and then also going into some examples of where we've been able to make an impact with customers. So starting with sustainability and why sustainability is part of this conversation. Realistically, what we're focusing on from a sustainability impact, and what I did was just kind of easily just Google sustainability, let AI kind of tell me what I'm looking for. And you'll see on here, it talks about the 3 dimensions regarding environmental, economic, and social. And realistically, what we're focusing on is the environmental and economical impact. Diving a little bit deeper, from an energy standpoint, the energy efficiency is one of the twin pillars for sustainable energy policy. And then over on your left, you can kind of see where it talks about basically looking at reducing resource consumption. So that's a lot of kind of where we're focusing when we have these conversations. So expanding on this, we wanted to kind of, this highlighting some customers we have worked with, but also any of you may have your own policies throughout your companies and stuff as well, but sustainability is a big initiative throughout most corporations, as it should be. And you'll see a lot of it ties into investing in energy efficiency, looking at resource consumption, using technology to improve that efficiency. So just wanted to kind of bring some validity to it just based on some experience that we've worked with as well. Expanding on just those customers, this is also just highlighting different industries as well, many of which you'll see here based in Alabama as well, that we've worked with and that are hoping to work with soon as well. But the area of dust collectors is pretty prevalent throughout most levels of manufacturing. So why do customers utilize dust collection? So it's around controlling emissions as might be driven by the EPA, improving and controlling indoor air quality as you might see driven by OSHA, or as part of a process dust collector like you'll see in kind of a cement space. They'll have raw mills and finishing mills that's utilized in the manufacturing process of those collectors. So those are the 3 categories that we typically see those in. There's different types of collectors. The main ones that we focus on is what's called a pulse jet baghouse. I'm not sure if any of you have familiarity with that, but kind of going through the operation. A vacuum system brings in dirty inlet air. It leverages baffles to evenly spread it throughout the dust collector. And then those baffles allow the air to be spread to filters that's catching contaminants. And then on the outlet, you have clean air being pushed out. And this is what they might look like in some plants, just to give a visual representation if you might have those in yours. So diving in a little bit deeper, one of the reasons they call it pulse jet is because of how the cleaning system works. So you have a header that holds the volume of air leading into a diaphragm valve that is operated by a solenoid valve. When that solenoid valve is energized, that diaphragm valve opens, allows air into the blowpipe, which then goes into a venturi system that flexes the filter and knocks off the contaminants in it. Visual representation right here just to kind of show. So on your left, you'll see the contaminants being captured on the filter, and then the one on your right, you'll see the air being pushed through the venturi and flexing the filter to knock the dust off. So the dust is then dropped to the bottom of the collector. So the energy impact of these systems. Typically what we're seeing is these collectors are major consumers, if not the major consumer of compressed air in most industrial facilities. Compressed air is one of the least efficient energies, causing only around 10 to 20% of that efficiency, the energy output that's caused to produce it, is actually utilized and converted into the compressed air, with the rest of it being lost during heat buildup and compression and distribution. And then inefficient collectors cause further strain and further demand on these systems and increase energy spend by our customers. So talking about inefficiency, and this is going into the cleaning system as a whole. So the technology that's utilized in these systems is a diaphragm valve technology that's been out since probably the 60s or so, and they've utilized that same technology based on simplicity. One of the things that is a degrading factor of that technology is some of the failure points and how it wears and differentiates from an operational standpoint over time. So as this valve starts to lessen and starts to become less effective, what typically we see is the operation or the operators of these systems will start doing 4 different things, and it's in a staged effect typically. So you'll have them increase the pressure of the system, taking a system maybe normally operating at 85 psi, driving it to 100, which causes more energy demand, more strain on the compressor. When that doesn't maintain a certain level of differential pressure for the operation of that system, then what they'll do is increase the pulse frequency, which is how often that's firing. So instead of firing 5 times a minute, maybe they're going to try to turn it to 10 times a minute to get it to clean those filters better and to lower that differential pressure of that system. When they still struggle with that, they'll increase the on time, and the on time is how long that solenoid is electrically energized. So typically the operation of it is supposed to be in the 150 to 250 millisecond range. We'll see customers jack it up to 400, 800 milliseconds, thinking that that longer time will actually clean the filters better. And it's actually worse for the systems when they do it that way. And then the last thing they'll end up doing is replacing the filters because all else has failed. And so you have a significant cost with the filters, significant cost with change out, and realistically those filters probably weren't bad at that time. So looks like some of my animations are delayed. They're supposed to go with it. So pressure, frequency, on time, and then filters, all equating in significant amount of cost. So where we've kind of gotten involved with this is about 10 years ago, one of our manufacturers introduced this pulse valve technology for this, which utilizes a different type of pilot than for the solenoid valve. We're utilizing what's called a 4-way pilot, which allows us to utilize air to shift both directions, so open and close. And one of the more important things is the air in the spring puts this valve in a normally closed position when it's not energized or when it fails. You'll see in a couple slides, the existing technology utilized in these systems is opposite. It fails open, and that has a big effect on systems. And I'll show that here in a slide. Key advantages, typically we highlight around 7 when we're talking to customers, but in this presentation, we're gonna be focusing around energy savings and filter bag life. Where our conversation really starts and ends is around what's called pulse efficiency. So when you see in this chart, we utilized an O-scope to trace the airflow of a MAC valve and airflow of a standard diaphragm valve, utilizing the same pressure and the same on time. And you see the blue line being a MAC valve allows it to get to full pressure because the differential pressure through that valve is very minimal. So this system is operating at 85 psi. You'll see that we get pretty much at that 80, 85 range there. whereas a diaphragm valve gets to 60. So you have about a 20 PSI pressure drop, and that's why on the previous slides you see that customers will start increasing the pressure to try to get it to operate more, just because the valve isn't being as efficient as it should be with the system. But the more important thing is how quickly we close. So if you look at how this kind of ends, and this is in like the 250 millisecond range, how quickly that closes as compared to a standard diaphragm design dragging out almost 100 milliseconds more. The reason that's important is through the venturi, there's basically what's called a wave or a ripple effect that allows to knock the dust off the collector. And when that is not sharp, that wave becomes very dull and not forceful enough to knock the dust off of the filter. So that's the challenge that a lot of customers will end up seeing. I have a video. Hopefully the format will actually allow it to work. So what you'll see in this video is on your left is a filter that is operated by a diaphragm valve. On the right, it's operated by a Mac pulse valve. Same collector, same on time, same pressure, same flow. Everything's the same except the valve technology on there. Let's see if this works. So we'll go through at least a visual representation from a static standpoint. So this is an example. This is actually an application where this is a sugar dust collector. And so this is in operation of a cereal plant. And you'll see clogged filters caked up with dust. What they did in this test is installed all new filters in the collector and only changed one valve row with the Mac valve as on that third channel there. And you can see in that center row, it's the third valve over, but it's driving that center row. You can see the cleanliness of that filter as compared to the other ones just after 3 weeks of operation. So think about the life of that collector and the life of that filter just by changing that valve. So that's kind of what you'll see. I can try to get, for anybody that's interested, I can show that video as well. It's pretty impactful as a follow-up. So on the filter life side of things and the sustainability with that, obviously when these filters get used up, they're typically thrown away. And the longer we can extend that life, the longer we can keep those out of landfills, the longer we can keep those in operations, and we can also reduce the amount of cost used on filters. So typically filters have a life rating of 100 pulses, 100,000 pulses to 150,000 pulses, depending on the type of filter used. And if we can expand that from, instead of doing 10 times a minute to 5 times a minute, and think about extrapolating that from a lifetime standpoint, we're really extending that life and reducing the amount of filters that are going to a landfill. So if there's measurements as far as what we're sending to a landfill, some of these collectors will have thousands of filters on them. So that's a significant amount going into landfills that we can potentially reduce from a time standpoint. Being an engineer, I'm pretty data dependent, so I like showing, and I'm going to utilize these last couple of minutes of the presentation to talk through some true data from applications. So this is a company called Compressor Energy Services. They're actually based out of the Northeast, and they worked with one of our counterparts and a customer to identify a baseline of existing collector. So you'll see in here, it's a 30 valve collector. They measured the amount of air demand on this collector being 42 CFM in the existing state, and equated that to about $7,000 in operation. Changed those 30 valves over to the Mac valve technology, did nothing else but change those valves. And what that ended up doing, let me see if there's, yep, laser. What that ended up doing is decreasing the CFM down to 19 CFM, or a 55% reduction, just by changing the valves. Then through that and monitoring that the differential pressure was staying lower, they were able to adjust the settings to increase the time in between pulses and then take that down even further to 11 CFM. So thinking about just a small collector of 30 valves, they were able to reduce the air consumption by 74% and save $5,200, changing that operation from 7,000 to 1,800 just on that collector. What they also found, and kind of what I highlighted earlier, is through the testing, when they were monitoring this flow consumption, one of the existing diaphragm valves failed. And how that works is when the valve fails, that valve is left open, so there's constant airflow going into that blowpipe and then going into that venturi, and really just wasting air. So this actually took the system that was around 40 CFM in normal operation up to 300 CFM just in that operation. And a lot of times these collectors are in tough places to where customers and operators won't necessarily see or know that it's down until they potentially bring down a compressor or until they go check it hours or days and stuff later. So the amount of energy that's caused just because the failure mode being a failure mode open is really significant to customers. And we've actually just introducing the valve technology that fails close has been a selling point to a lot of customers to make that impact to avoid some of these issues. So mentioning data and kind of examples, just wanted to kind of go through a couple of examples. So this is a pharmaceutical manufacturer, and just working with them on a small collector, we were able to help them see $5,000 in energy savings, $2,400 in filter life savings, just looking specifically in those realms. On the paper mill side of things, this is specifically in a powerhouse of a paper mill. With them, we were able to show about $1,700 in savings and then $2,500 in filter life savings. And then also there's an operational and safety aspect too. They had to utilize a crane to access this from being able to change out these valves, change out these filters, and being able to put a more reliable valve technology and extend the life of the filters. They don't have to pay that cost and handle any of the safety requirements of utilizing a crane and getting operators and stuff up there. One that might be pretty relevant here in Alabama, steel. So these are two different examples, two different steel mills that we've worked with. The one on your left is specifically focusing on the amount of on time from a flow standpoint. So these valves, when they were being pulsed, were open about 30 seconds compared to milliseconds. And these valves are about 3-inch blowpipes, so significant amount of cost through that. So just looking at 24 valves and changing this valve technology, we were able to help them save $66,000 there. And then the one on your right is actually monitoring true leakage through the existing valves, because the diaphragm valves will crack and wear over time. So you'll get different levels of leakage through. So on that collector, they were able to see $120,000 just in leakage, not even actually improving operation there. So significant numbers, and these are just individual collectors at a steel mill. Last kind of example we have here is a gypsum plant, and this is what's called an imperial mill. They have a hot side, and so there's a hot A and a hot B. So with this customer, we were able to work with them and upgrade the valves on one of the sides on their B side and keep the existing valves on the A side. So really have a true one-to-one test in a mirrored system. And this is their data. They put full flow meters monitoring that real time. And you're able to see in that chart from an average cycles per day, so an average pulse per day, 250 as compared to 700, equating to about $5,000 operational costs from an air standpoint compared to $27,000. So doing nothing else but changing the valves there, significant amount of savings, which allowed them to justify upgrading the A side as well to the same valves. So this is looking at individual collectors, maybe 2 collectors in this example, but really where it makes the biggest impact and where I wanted to kind of end is one of our customers that we've worked with here locally and nationally and globally is Emirates. And Emirates actually drove this demand. You'll see kind of on the top right, this is an internal presentation that they had where they identified compressed air being known to be the least efficient utility industrial plants, and also the largest user of compressed air within their facilities. So they had an initiative on the energy and environmental side of things to really attack and see, is there ways that we can improve that? So they were able to be awarded the best of the betters for the better buildings with the DOE. And this is kind of a screenshot from that presentation walking through what they did. So being able to lower the operating pressure from 100 to 85 PSI, because that difference isn't going to, as you saw on the previous slide, that difference isn't going to change the effect of how those filters are cleaned. It's really around the actual operation of the valve, the control settings. So they lowered that by 15 PSI. They were able to shut down one of their compressors there, change the control type, pulse on demand. So there's two different types. There's a pulse on time and a pulse on demand. Pulse on demand means it only fires when it's supposed to, as dictated by a differential pressure. So they changed that, implemented MAC valves, and identified just through those valves were 20% air consumption reduction there. And then through that first phase, they were able to shut down 2 compressors and save $68,000. And that led to a North American initiative where they identified 14 gigawatt hours of reduction that could be provided and 67,000 metric tons of CO2 eliminated. So how this can transform from just one collector to a plant-wide into a corporate-wide or multiple-site initiative is really the impact that we're seeing globally from an energy standpoint, and where I want to spend a little bit of time here to make sure that you are aware of it and see if there's anything we can do to help. So, questions?